Good afternoon, everyone. Can you hear me okay? Can you give me a thumbs up? Okay, great. So before I start with the material that I prepared for today, any questions you might have on what we have taken up so far last week and last Tuesday? Any questions? I hope you've had a chance to go through the material published in UVLE also. I mentioned this last time that if you go to these sessions without any inkling what is going to be discussed, baka mahihirapan kayo. No? Better if you read the published material beforehand. Anyway, if there are no questions, I'm going to proceed with what I prepared for this afternoon. Yeah, so this afternoon, we're going to be talking about bipolar junction transistors. This material was, or BJTs were already introduced to you in EEE 123, but the way BJTs were taught in EEE 123 was through a behavioral model. In other words, in 123, we did not discuss how the BJT actually works. So it's going to be a little bit different this time because we're going to have a discussion about how the BJT actually works. So this is still a review of EEE 123. So here I show the simplified structure of two types of bipolar junction transistors. You have your NPN and you have your PNP. In the simplified structure, my NPN consists of a P-type region sandwiched between two N-type regions. And then in the PNP transistor, it's the opposite. You have an N-type region sandwiched between two P-type regions. The sandwiched portion, you call that the base region. So in the NPN, you have a P-type base. In the PNP, you have an N-type base. Take note that this area is actually very narrow. That's actually very narrow. It's not shown here to scale. The base region here is blown up, no, or is exaggerated. But manipis na manipis talaga yung base region na yan. Okay, we have two junctions in our BJT. You have two junctions. You have what we call the emitter-based junction. And the collector-based junction. So these are two PN junctions. So we took up the PN junction last time. So in this particular case, this is the emitter-based junction. Let me use a different color. This is my emitter-based junction. And then this is my collector-based junction. Now, the more typical structure of your transistor is shown here below. This is what we call a planar transistor, a planar NPN transistor in this particular case. Okay, the reason why we call it planar is because all of the terminals can be accessed from one plane. So this is a cross-section. This is a cross-section. Okay, if you take a look at the 3D view, the 3D view will look something like this. Sorry. It looks something like this. That is the 3D view. So this is your emitter region. This is your base region, which is larger than your emitter region. And this is your collector region, which is the largest region. And if you take a look at the junctions, these are your junctions. This is your emitter base junction. This is your EB junction. And this is your collector base junction. Okay. Take note that the collector base junction is much larger than the emitter base junction. So the CB junction is much larger than the EB junction. Okay, here are again, this is still a review of 1, 2, 3. Here are the reference directions for currents for an NPN and a PNP transistor. In your NPN transistor, your base current and your collector current are entering the terminals, and your emitter current is leaving the terminal. In your PNP transistor, it's the opposite. Your base current and your emitter current are, your base current and your collector current are leaving the terminal, and your emitter current is entering the terminal. So the current directions for your PNP, these are the normal current directions, and the current directions for your NPN are opposite each other. When we draw the PNP transistor, usually we draw it with the emitter at the top. So in the NPN transistor, we usually draw it with the collector at the top. Here, we usually draw it with the emitter at the top. And this is because in circuits with both NPN and PNP, usually they share a single power supply, and you follow the direction of current from top to bottom. That is why it is usually drawn this way. Because if we draw it the normal way, then your direction of current will be from bottom to top. Okay, with respect to the voltages, the terminal voltages for your NPN are as follows. From collector base, we have plus minus VCB. And from base emitter, we have plus VBE. And from collector to emitter, we have VCE. So those are that is how we describe the terminal voltages of your NPN. On the other hand, for a PNP, we reverse the subscripts. If it is VBE in the NPN, it is VEB in the PNP. In the NPN, it is VBC. Here is going to be, in the NPN, it is VCB. Here is going to be VBC. And here it is VCE. Here it's going to be VEC. So that's how we normally describe the voltages, the terminal voltages in your PNP and your NPN transistor. Take note that the transistor in a circuit acts like a supernode. If you recall the definition of a supernode, okay? A supernode is not capable of accumulating any charge. Therefore, the currents that enter that node must be equal to the currents leaving that node. In both cases, IE will be equal to IC plus IB. In the case of the NPN, IE is leaving, IC and IB are entering. In the case of the PNP, IE is entering, and IC and IB are leaving. So this relationship will always be true. IC is equal to, or IE is equal to IC plus IB. Are there any questions so far? Any questions? Okay, I hope you're still following. Oh, I'm missing a slide. Okay, let's consider an open-circuited. No, sorry. First, let me take up the modes of operation. So let me just draw a table here. Okay, your mode of operation will depend on whether your junctions, that is your collector base and your emitter base junctions, are forward biased or reverse biased. So this is, let's say this is your emitter base junction, and this is your collector base junction. We have a particular mode of operation. So let me see if you recall. So this is still EEE 123. What do you call the mode of operation when the emitter base and the collector base are both reverse biased? Can I hear a shout out from anyone? Anong tawag dito pag parehong reverse biased?
Sir,
Anyone?
cut off po ba?
That's right. No, thank you. Thank you for that answer. So when they're both reverse biased, this is what you call cut off. Okay, what about when they are both forward biased? Can I hear somebody else?
Sir, saturated po ba?
Yes, that's right. Saturated. Okay, what happens if the emitter base is forward biased and the collector base is reverse biased? Ano yung mode na yan?
Sir, active po, sir.
Okay, thank you for those that answered. Ano? This is active. Maybe more specifically, you call it forward active, because if the emitter base is reverse biased and the collector base is forward biased, you call this reverse active. When we operate in cutoff or saturation, this is usually for switching circuits. Or digital circuits. When we operate in the active mode, usually this is for linear or analog circuits. Active mode is usually linear circuits. Okay. And when you operate in reverse active mode, usually it's because you made a mistake. So the reverse active mode usually is not used. No? Usually not used. Kadalasan, if you find a transistor operating in the reverse active mode, it's because nabaliktad nung nag-assemble yung collector at saka yung emitter. So yung emitter ginawa niyang collector and vice versa. Kung yung construction ng transistor natin ganito, then conceptually, your emitter and collector can be interchanged. But the fact is, the construction of your transistor is not symmetrical. It's something like this, in which case you cannot change the collector and emitter. The emitter has a much smaller area than the collector. The collector is supposed to collect current. That's why it has a big area. Okay? So if you reverse the two, your emitter, which has a small area, will be the one collecting the current. So it will not be as good a transistor. That's why we don't usually use the transistor in reverse active mode. Any questions? Okay, I'm for the rest of this discussion, I'm going to focus on this active mode. So dito tayo magpo-focus for today. But when we take up the transistors again in module 2, we're going to discuss in more detail the cutoff mode and the saturation mode. I need again a page. Okay, let's consider an open-circuited okay, NPN transistor, no? NPN transistor. Okay. So I have again we will use the simplified construction para mas madaling i-conceptualize. I have two junctions. So this is my emitter. Okay, this is my base, and this is my collector. So this is my emitter-based junction, and this is my collector-based junction. Okay, open-circuited. What will happen the instant this transistor is created? By the way, no. So this is N-type. Okay, this is P-type, this is N-type. Usually in a transistor, the the emitter, okay, the emitter region this is heavy dope. Okay, the base region, this is very lightly doped. And then your collector region, okay, this is doped at a level between the emitter and the collector. So dope at a level between emitter and base, rather, not collector, no, between the emitter and the base. So itong emitter region, malaki yung value ng ND, no? Your donor impurity concentration. Dito sa base region, maliit yung value ng NA. Dito naman, the value of ND will be somewhere in the middle of ND here and NA here. No? In other words, maybe this is a regularly doped semiconductor. Now, what's going to happen? You're going to have two depletion regions. Okay? You're going to have a depletion region at the emitter-based junction. I'm going to show it this way. Okay. And you're going to have a depletion region also at your collector-based junction. I'm going to show this way. So this is these are both depletion regions. Let me try to okay. So these are depletion regions. Okay. Okay, as you can see, the depletion region is going to extend into the base more than it extends into either the emitter or the collector. Can anybody guess why? Can anybody guess why? No? Pag tinignan mo rito, kita mo, no, mas malapad yung depletion region sa base kaysa sa emitter o kaya sa collector. Dito, no, ang nipis ng depletion region sa N side, dito malapad yung depletion region sa P side. Ganun din dito, no? Manipis dito sa N side, malapad sa P side. Can anybody guess why?
Because how the regions are doped, sir.
Yes,
The base
exactly.
region has a very lightly dope.
Exactly, no? Very good, no? Because of how the regions are doped, no? If your base region is very lightly doped, that means you need a bigger area for the holes here to neutralize the electrons here. The same reason here, no? If this is very lightly doped, you need a bigger area for the holes here to neutralize the electrons there. Okay. Now, whenever you have a PN junction, open circuited, no? This is open circuited, you're going to have a built-in potential. So I'm only going to show here the EC, ano? Papakita ko lang sa inyo yung EC. So if I take a look at EC, this is the bottom of the conduction band. It's going to look something like this. Okay. From here, so this is my depletion region. I'm going to get band bending this way, right? Because in a PN junction, the potential energy for electrons will increase at the P side with respect to the N side. So I'm going to get band bending this way. So here I'm going to get a built-in potential. Let me call this VBI1. Okay. If you recall from last meeting, the definition of VBI or the formula for VBI, okay, this is V of t ln of nd na over ni squared. That is the formula for your built-in potential. I'm also going to get a built-in potential in my collector base region. So my question is this: where will the built-in potential be larger? Will it be in the collector base or will it be in the emitter base? Is anybody willing to guess? Saan magiging mas malaki yung VBI? Dito ba sa depletion region na to o dito sa depletion region na to?
Sir, guess lang po sa emitter base ba po pa?
Yes, that's right. Bakit mo gines yun?
Sir, because yung emitter is more heavily doped than the collector region.
Yes, that's right. Ano? Kasi yung ND mo sa emitter, mas malaki sa N of D dun sa collector. So naturally, mas malaki yung magiging value ng VBI dun sa emitter base. Ano? So if I take a look at my bending now, okay, it's going to look like this. Ano? Ito maliit lang, and finally it's going to taper off. No? So ito yung VBI2 ko. So this is the energy band diagram. No? This is the EBD if open circuit. Okay, if I take a look at EV, ang EV susunod lang dito sa EC. No? So EV is the top of the valence band. It's just going to follow. It's just going to follow EC. Okay. And you're going to have a Fermi level. Hindi ko na mapapakita yung Fermi level. Ano? But you're going to have a Fermi level. Well, I can't show it anymore here. No. Yeah. You're going to have a Fermi level somewhere here in the middle. No. Maybe I should show it. No. I need to modify this a bit. So I'm going to have a Fermi level that will probably be somewhere here. No? Anyway, your Fermi level will only be one level, no? Is of F. So that's what your energy band diagram is going to look like. Okay, are there any questions? Any questions so far? Okay, I'm going to discuss with you the current components in an NPN BJT. So this is going to be biased in active mode. Okay, what did we say was active mode? We said active mode means that the base emitter was forward biased and the collector emitter is reverse biased. So if you notice, I apply a base emitter voltage, okay, and assuming that there is no voltage drop across the quasi-neutral regions, we call it, this is supposed to be a neutral region. Sorry. Yeah, well, I don't want to introduce any new terms, but assuming there's no voltage drop here and here, okay, then this VBE will be applied across the depletion region. And we also assume low-level injection, that is that this VBE is smaller than VBI. So this tends to forward bias the base emitter junction. Notice that the positive terminal is applied to the P and the negative terminal is applied to the N. Ito namang VCB, this will reverse bias the collector junction. You notice the positive terminal is applied to the N and the negative terminal is applied to the P. Okay, so reverse bias dito, forward bias dito. Okay, anong mangyayari ngayon okay, these are my depletion regions. Anong mangyayari ngayon dun sa energy band diagram ko? So I'm going to show again here just piece of C. Okay, if I take a look at piece of C, because of the forward bias, my built-in potential is going to become smaller. Remember that in a forward bias PN junction, okay, the bending becomes smaller, and that is what allows diffusion. When it's open circuited, you have drift and diffusion canceling each other out, but when it becomes smaller, then you have now more diffusion than drift. I explained this in the last meeting. So if I take a look at E sub C, okay, that's going to become smaller. So it's going to look something like this. So this height is now going to be essentially going to be VBI minus VBE. On the other hand, this reverse bias will make my band bending bigger. Lalaki yung band bending. So if I take a look now, this is going to go down all the way here. And this is now, so this is VBI1, this is VBI2 plus VCB. Okay. By the way, I forgot to mention something in the previous diagram. Note that this is going to be W, and this is going to be the effective width of the base. Itong part ng base is already depleted of charges. Itong part ng base is already depleted of charges. Yung meron na lang charge carriers will be the middle part. That is W, and we call that the effective width of the base. And that's going to be very, very small. If to start with, manipis na yung base region, nabawasan pa yung width ng base region because of the depletion regions. Okay, so in effect, this is my W. Okay, let's take a look at the current components. So this is forward biased. No? My emitter base is forward biased. What is going to happen? I'm going to get diffusion. My diffusion is going to how do you say this? Sasapawan ng diffusion yung drift. No? I'm going to get diffusion. And what is going to diffuse? I'm going to get electrons from the N diffusing toward the P, and holes from the P diffusing toward the N. So I'm going to get electrons this way. Electrons. And I'm going to get holes this way. Okay. My holes are going to contribute to the emitter current. So this is going to contribute a current, these holes. So let me show it this way. Okay. And I'm going to call this my emitter current, IE, due to holes, due to P. No? And that emitter current will terminate at the base. So I have holes coming from the base region that will diffuse now, into the emitter region, no? Eventually forming part of my emitter current. Okay, so I have electrons moving toward the right. That is now going to contribute a current due to electrons. Okay, so I have a current due to electrons this way. Okay, this is called IE due to N. Now, can I ask, what is the direction of this current going to be? Is it going to be right to left or left to right?
Left to right po, sir.
It's going to be left to right?
Yes.
Think about it. These are electrons flowing, no? These are electrons flowing.
Right to left.
Right to left, yata, sir.
Okay, that's right, no? So I just wanted to make you think about it, no? So because my electrons are flowing through the right, remember current is opposite the direction of electron flow. No? So this IEN is going to be right to left. That IEN is going to be right to left. Okay, because this is very lightly doped, itong area na to is very lightly doped, my IEP is going to be very small. No? So that most of my emitter current will just be due to the electrons. Kasi lightly doped to, no? So halos walang charges na nanggagaling dito. Halos walang holes na nanggagaling dito. Yung value nito, IEP, magiging maliit na maliit, no? So itong IE ko, halos lahat niyan, ito lang IEM, no? But I'll get more into that later on. Okay, anong mangyayari dito sa electrons na to? No? Anong mangyayari dito sa electrons na to na pumapasok sa base area? Okay. Yung iba sa kanya, okay, is going to recombine. So this is a recombination. No, this is recombination. In which case, part of it, due to recombination, will form part of the base current. So this current here is due to recombination. But that's going to be very small. No? And the reason why that's going to be very small is when the electron is crossing over, okay, before it has a chance to recombine. So you imagine your electron is crossing over. Because before it has a chance to recombine, it can enter into this other depletion region. So ito yung electron natin, no? Ito yung electron. Okay. Before it has a chance to recombine, it might find itself here. And when it finds itself here, okay, your potential energy here is going to go down, and therefore the difference between this energy and the potential energy will be kinetic energy. And so this electron is now going to move very fast toward the right. It's going to gain kinetic energy. So as it goes toward the right, this is its kinetic energy. So you might think of it as parang yung electron parang biglang nahuhulog, no? Or you might think of this as a hill. Para itong hill, all of a sudden yung electron will roll down the hill very, very quickly. And that electron will find itself in the collector region. So you have a component of current now. Okay. This is now I C due to N, which is composed of the electrons that end up seeing the depletion region here and being drawn very fast toward the collector. Kasi ang tarik nito, no? Dahil sa tarik nito, itong electron na to, pag pasok niya dito sa depletion region na to, biglang lalabas na lang siya rito kaagad and will form part of the collector current. Okay, so that's what's going to happen. So this due to recombination is going to be very small. Okay, now we have another component of current. Since this is reverse biased, since the collector base is reverse biased, there are going to be minority carriers here. So what are your minority carriers here? That's going to be P that will be attracted toward the N. That's tama, no? Yung minority carriers here that will be your P that will be attracted here toward the base, no? Because of the negative bias here. So your positive charges here will be attracted toward the negative terminal of your power supply. But that is due to intrinsic carriers. So you're going to get a very small current here, and we call this ICO. So this ICO, this is essentially, this is reverse saturation current. Okay. So those are the components of your current in your transistor. Any questions? Any questions so far?
Sir?
Yes,
Sorry, clarify ko lang po sana. Paano po nakaka-generate ng current ang recombination, sir?
No, recombination is actually when your holes and your electrons see each other and become becomes a neutral particle.
Oh, so paano po nagkaroon yun pong sa one of the currents coming out of the base current? Paano po naging current due to recombination?
What I mean by that is you have a constant amount of electrons. You're going to have a constant amount of electrons that are entering into this area, and that will recombine with the holes in this area. No? That's all, no?
Oh, okay, sir.
So yun lang, no? And that's going to constitute a current, and that current is going to affect this value of I sub B.
Oh, okay po. Thank you, sir.
But that's a very small fraction of these electrons, no? Na mag-recombine dito. Kasi yung electrons, pagdating una-una itong W na to, maliit na maliit, no? So more probable, bago siya magkaroon ng chance na mag-recombine, makikita na niya tong depletion region na to, tapos mahuhulog na siya dito. Lalabas na kaagad siya sa collector. By the way, that's why you call this the collector. Kasi yung collector, yan yung taga-salo. Yung emitter, siya yung taga-bigay. We're talking here about electrons, no? The thing that might be confusing here is we're talking about electrons, and the current direction is opposite the flow of electrons. But your electrons are flowing from left to right. Yung iba magre-recombine dito, but the bulk of it will cross. Then all of a sudden, hihigupin itong collector. That is the basic carrier action here. Now, if this were a PNP, ang PNP, then you call this your majority carrier now, no? Your electron. In a PNP, the bulk of your current will now be due to holes. Because this is going to be P-type, this is going to be N, this is going to be P. So it's going to be holes now that will diffuse across the base, okay? And then some will be recombined, but the other will be swept toward the collector, and then the collector will collect these holes. So ganun yung action sa PNP. And then the direction of current is going to be to the right because the holes are positive charges or equivalent to positive charges. And so your current is in the same direction as the flow of your holes. So but otherwise all of the current components will be similar. Okay.
Sir, question.
Yeah. Please. Go ahead.
Di ba sa mga transistors, meron pong beta? Saan pumapasok yung beta dyan?
I'm going to get to that. No, I'm going to get to that. Okay, kasi inaalala niyo sa 1, 2, 3, ano? Okay, balik tayo rito, no? Yung IE is equal to IEN plus IEP. IE is equal to IEN plus IEP. So your emitter current will have a component due to electrons and will have a component due to holes. We're talking here about an NPN transistor, no? NPN transistor. Again, just to qualify, in active mode. Because these relationships, I'm sorry about that. These relationships will not be valid in non-active mode. No? So IE is IEN plus IEP. Now, because your base is very lightly doped, IEN will be very much greater than IEP. Okay? And therefore, IE will be approximately equal to IEN. In other words, ito, ginawa na nating negligible tong IEN. No? So this is for an NPN. No? For a PNP, it will be the opposite. No? For PNP, it's going to be IE is approximately equal to IEP. Kasi ang N naman yung magiging negligible. No? IEN is going to be negligible. Okay, let me define what we call emitter efficiency. Okay, we give this the symbol sigma. Okay, and this is the percentage of emitter current due to your majority carriers. Okay. So if you consider the NPN transistor, your sigma is equal to IEN because your electrons are your majority carriers divided by IE. So yung emitter efficiency, okay, that is the percentage of this, which is due to this. So your emitter efficiency is actually just the ratio of IEN over IE. And we want this to be very close to 1. We want that to be very close to 1 para maging totoo to. That IE is approximately equal to IEN. Okay, then we have what we call the base transport factor. Okay. The base transport factor is alphas of T. And this is the percentage or fraction. Well, when I say percentage, I mean fraction. A fraction of a, so ito, isipin na lang yung fraction yan, hindi percentage. No? Fraction of emitter majority carriers that reach the collector. The fraction of the emitter majority carriers that reach a collector. So here I'm talking about these electrons. These electrons, these are your majority carriers, no? Kasi yung holes natin negligible, no? So these are my majority carriers or electrons. What fraction of this will actually make it here to the collector? No? What fraction of these electrons will make it to the collector? And that the answer to that is going to be ICN over IEN. No? That is the ratio of ICN over IEN. So alphas of T is equal to ICN over IEN. And we also want, no, this is for a good transistor, a good quality transistor, we want alpha T also to be close to 1. Finally, we define what we call the transistor alpha. Alpha is defined as your emitter efficiency multiplied by your base transport factor. So if we substitute, emitter efficiency is IEN over IE, and your base transport factor is ICN over IEN. So this will cancel out. So this is now ICN over IE. ICN over IE. So that is the ratio of this current to this current. The ratio of this current component to this current. And we have a special term for this. No? Alpha is called your common base DC current gain. Now, later on, you're going to find out what we mean by common base. But this is your common base DC current gain. Okay. So you have the formula ICN is equal to alpha multiplied by I sub E. Okay. Now, if you take a look here, I sub C is ICN plus ICO. Itong I sub C, you have two components, ICN and ICO. I sub C is equal to ICN plus ICO. And ICN, we said, was alpha multiplied by IE. Okay. From here, no? ICN is alpha multiplied by IE. Now, itong ICO, the reverse saturation current, so this is, I mentioned this earlier, this is due to intrinsic carriers. And this is extremely small, no? Extremely small. So we know that the reverse saturation current for a diode, if you remember from the last lecture, this is anywhere from 10 to the minus 10 to the minus 9 to 10 to the minus 15. That's how small ICO is. Your intrinsic carrier. So for all intents and purposes, IC, or for all practical purposes rather, is approximately equal to alpha multiplied by IE. So effectively, nineglect na natin to. Right? And therefore, this IC, which is completely composed of ICN, will just be alpha multiplied by IE, which is this component of your current. Okay, now recall from KCL, we know that I of E is equal to IC plus IB. Right? And I of E is IC, from this equation, I of E is IC divided by alpha. So this is IC over alpha, yun yung value ng I of E, is equal to IC plus IB. So here we can derive an expression relating IC to IB. Right? So you have IC, from here you have IC, 1 over alpha minus 1 is equal to IB. Okay, or IC is equal to, okay, this is 1 minus alpha over alpha, no? Or alpha, this is going to be alpha over 1 minus alpha multiplied by IB. And this answers the question earlier. This is now what we call your beta. That is what you call your beta. So you have IC is equal to beta times IB, where beta is now your common emitter DC current gain. This is your common emitter DC current gain. So what are the typical values of alpha? No? So we said here, the sigma is very close to 1. The base transport factor is very close to 1. So expect alpha, which is sigma times alphas of t, to also be very close to 1. Of course, it will be smaller than either of these two, but it will also be very close to 1. No? So if you take a look at alpha, typically alpha would be anywhere from 0.95 to about 0.995. If I plug this into this, no? I wrote this wrongly, no? Mali pagkasulat, sorry. So alpha is here, no, nakalimutan ko yung signs na yan. Is anywhere from 0.95 to 0.99, no? 99, sorry. No, 0.995, sorry. Okay, so if I plug this into this and try to compute for beta, my beta would be anywhere from 50 to about 200. Okay. That's going to be my beta. No, sorry, 20. No, 5 over 100 is 20 to 200. Tama nga ba? Yeah, 20 to 200. Okay? So anong ibig sabihin nito, no? For a very small amount of base current, you get a very large amount of collector current. So if I maintain myself in the active region, if I inject a very small amount of current into the base, that is going to translate into a very large current that is at the collector. Okay. Are there any questions so far? Okay. Any questions? Okay, so we have our simplified transistor model. Which is the model that you have been using in EEE 1, 2, 3. No? So if I have my base, my emitter, and my collector, okay, between my base and emitter is just a PN junction. So this is for an NPN. No? This is for an NPN. And between my collector and my emitter, I have a controlled current source. Okay, where the value of my controlled current source is equal to beta times I sub B, where I sub B is the current entering my base terminal. Okay. And if I get the base to emitter voltage, that will just be the voltage across my PN junction, which for simple calculations, you can just assume to be about 0.7 volts. This is for simplified calculation. So VBE is approximately equal to 0.7 volts for simplified calculations. Okay, but later on in this course, we will consider a more accurate calculations for VBE. If you take a look at the common emitter characteristic curve of an ideal diode, of an ideal transistor, the common emitter characteristic curves okay, if this is an ideal transistor, meaning to say IC is equal to beta times IB. So how is that going to look like? Okay, your characteristic curve, this consists of a plot of IC versus VCE. Plot of IC versus VCE. And this is just going to be a family of horizontal lines. A family of horizontal lines. Each line corresponding to a specific value of IB. So for example, if this is IB1, then this point will be beta times IB1. No? The value of IC will be beta times IB1. This is IB2, is going to be beta times IB2, and so forth. No? IB3, this is beta times IB3. Where IB3 is greater than IB2 is greater than IB1. And notice that VCE has no effect on I sub C. If this were a PNP transistor, instead of VCE, this will be VEC. Yun lang yung kaibahan. No? Instead of VCE. Remember, pag PNP transistor, nagbabago lang yung, nagsiswitch lang yung ano natin, no? Yung subscripts natin. Okay, if you take a look at the actual curves, it's going to be slightly different. No? If you take a look at your actual curves, if this is IC and this is VCE, again, it's going to be a family of curves, okay, but it's going to be slightly different. So this is how your family of curves is going to look like. So this is going to be for IB1, IB2, IB3. In general, your collector current is equal to beta times IB1. So here it's beta times IB2. Here it's beta times IB3. Okay. However, your active mode is only here. Ito lang yung active mode natin. Later on, you're going to find out that when it is in this region, this is actually in saturation already. No? So itong region na to, this is a saturation. Okay, and then the other thing that you're going to find out is that here, this is horizontal. Okay, that is horizontal, but okay, but here there is going to be a slight slope upward. Okay, why is there going to be a slight slope upward? Because I'm going to go back to this, no? Habang lumalaki yung VCE, if I continuously make VCE larger, no? So we're talking here about VCE. If I make VCE larger, while VBE is constant, then that means VCB is getting larger. No? If VCB gets larger, then this drop will get bigger, and this W will get smaller. Again, no, habang lumalaki yung VCE, lalaki itong VCB, lalaki itong drop na to, liliit itong W na to. Kung mas maliit itong W na to, there are going to be more electrons that will be swept toward the collector. The chances of the electrons recombining here in the base will even become smaller. And so more electrons will collect at the collector. And that's why there's going to be a very slight upward increase in the slope of this curve. So these are your actual curves. So this is again for an NPN transistor. This is for an NPN transistor. Okay, now recall the diode-Shockley equation. The diode-Shockley equation. Okay, so we said that your diode current, so this is I sub D, and then this is V sub D. We said your diode current is equal to your reverse saturation current e to the V sub D over eta V sub T minus 1. Okay, let's assume that you have a good quality process and that eta is equal to 1. So I sub D is just equal to I sub S e to the V sub D over V sub T minus 1. Now for normal values of V sub D, e to the V sub D over V sub T is going to be very much greater than 1. And it's very easy to show that. For example, if V sub D is 0.7, V sub T at 300 degrees Kelvin is 0.026, 0.7 over 0.026, that's a large number. And you raise e to that large number, you'll get a much larger number. No, you're going to get a number that is something like For example, kung ito 0.7, ito 0.026, that's almost like 5 times 10 to the 11, which is very much greater than 1. No? Meaning to say, I sub d, for practical purposes, is just I sub s, e to the v sub d over v sub t. Now note that, okay, your PN junction, your base emitter is a PN junction. No? Your base emitter is a PN junction. Okay. Therefore, your emitter current, your IEN, emitter current due to electrons, will be proportional to your base to emitter voltage. Okay. In fact, we can write IEN is equal to, okay, IS, no, let me first say, no, IEN is approximately equal to I sub E, right? IEN is approximately equal to I sub E, which is equal to, we can write this as equal to I sub S, e to the VBE over V sub T. So this is applying the Shockley relationship to your base emitter. Okay, and this I sub S, we now call this the transistor scaling current. Okay, just like your reverse saturation current, this is very small. Okay, so this brings us to a more refined model for the NPN transistor in active mode. So if this is your base, this is your emitter, this is now VBE. Okay. Okay, so what is this, no? This is equal to alpha times, sorry. This is equal to IC over alpha, no? IC over alpha. Because IC is equal to alpha IE. So I have here a controlled current source. Okay. Where this controlled current source now is going to be I sub S over alpha e to the VBE over V sub T. And this is going to be your collector. Okay, I'm going to stop there. No, that's all I wanted to cover for now. No? So you're going to learn more about the transistor in subsequent modules. So there's going to be an explanation of transistors beyond this in module 2, and then in module 3, you're going to go to even more detail of the BJT, and then module 5 and 6, you're going to be seeing BJTs in amplifiers and in frequency dependent circuits. Any questions? So that's it, no? As always, I will leave when you can leave now if you have no questions, and I will leave when I will close the session when the last person leaves. No? So that's all for this afternoon. Thank you.
Thank you, sir.
Thank you po.
Thank you, sir.
Thank you po, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you po, sir.
Yeah, you're welcome.
Sir.